we started looking at acceleration on what type of graph? Velocity versus time graph. The slope of that graph tells us acceleration. We can also see acceleration on a position versus time graph, but we can't calculate it, right? Because it's a curve. So we know what's happening on a position versus time graph, but the acceleration can actually be calculated on a velocity versus time graph. So we need to kind of review the overall definition of acceleration. It's any sort of change in velocity, right? We talked about this a little bit, and we gave the rule of thumb for acceleration when they're slowing down or speeding up. But we need to remember that acceleration can be positive or negative. Okay? Just because acceleration is negative does not necessarily mean that my object is slowing down, right? If I am speeding up in the negative direction, my acceleration would be negative, right? If on my graph I was in the negative direction, speeding up, my acceleration would also be negative, right? My slope in that situation is negative. So I can't get you to try to think about negative acceleration always means slowing down, because that's not the case, okay? So the rule of thumb I gave you earlier, I reprinted it here, but if my object is slowing down, the acceleration has the opposite direction of the motion, okay? Or the sign of the acceleration is opposite that of the velocity. So I want to prove that here. We're going to prove that mathematically with this equation here for acceleration. You can go ahead and put this on your equation sheet if you want. We're going to get another one that's slightly, that we'll use slightly more, but I'll show you what this means. The little line over the A, do you know what that means? It just means average. Okay, and that's always what we're going to calculate is average acceleration. I put it there because your book says it. I don't necessarily write that line really ever again, so I think you can leave it off and be fine. But acceleration is equal to change in velocity over change in time.
So do you suggest writing this one?
So remind me here what the delta means. Change in, and specifically what minus what? Delta always means final minus initial. So if I'm looking at acceleration, it's always going to be velocity final minus velocity initial over time. Okay? We're going to start seeing these variables here with an F and an I. What do you think those mean? Final and initial, right? Final and initial. So velocity final minus velocity initial over time.
That's the one that we'll use more.
No, I'm going to give you an even more rearranged one that we'll use a little bit more often. But velocity final minus velocity initial over time. Is velocity initial always going to be 0? No, not necessarily. Time initial will always be 0, so we don't really write the change in time. But velocity initial will not always be 0, so we need to make sure we have that prepared, okay? And also when we read problems, it usually tells me they go from 10 meters per second to 15 meters per second. We've got to be really careful about which one's the initial and which one's the final, right? So that we put them in the right order in our problem. But what are the units then for acceleration? Do you remember? Very good. This is meters per second, and this is seconds. So it comes out to be meters per second squared. Okay, or if you looked at it, some places write it meters per second, right? I don't love that version of it, but meters per second squared needs to be how we write that, okay? It will be very, very rare from now on that we'll really be dealing with kilometers per hour. Our acceleration most of the time has to be meters per second squared, which means my velocity needs to be in meters per second. So we can't have we wouldn't normally have an acceleration that's kilometers per hour per second, right? It would apply. I could do that because what it's saying is that we're changing this many meters per second every second, right? If my acceleration is positive 3 meters per second squared, what that's telling me is that with every second that goes by, my velocity is increasing by 3 meters per second, right? I'm going from 3 meters per second to 6 meters per second to 9 meters per second. So if I started at rest and I had an acceleration of 3 meters per second squared, After 1 second, I'd be going 3. After 2 seconds, I'd be going 6. After 3 seconds, I'd be going 9. Does that make sense what acceleration really means? It's telling you how fast your velocity is changing. So you could realistically have an acceleration that's 3 kilometers per hour per second, because that means with every second that goes by, my acceleration is changing 3 kilometers per hour. Right? So it still works, but it's not as clean, right? We still like to have our units be matching in that way. Okay, let's go ahead and try one here. A sprinter increases from 5 meters per second to 7 meters per second over a period of 1.25 seconds. What's my average acceleration? We need to kind of understand that acceleration and average acceleration is still the same thing. Right? Or we're going to solve them in the same way. If I have my equation A equals change in velocity over time, right? Or acceleration equals final velocity minus initial velocity over time, which one of these is my final velocity? 7.5. So just because 5 comes first in the problem, we're not going to go 5 minus 7.5, right? We've got to do final minus initial. 7.5 minus 5 over 1.25 gives me 2.5 over 1.25, which means my acceleration is positive 2 meters per second squared.
You don't have to put the...
Yeah, I don't have to put the plus, no. Nope. As long as you leave it positive, right, my assumption is then that I'm positive. So let's see, does that match the rule of thumb? Right, rule of thumb is if my object is slowing down, my signs won't match. But in this case, is my object slowing down or speeding up? Speeding up. So my acceleration and my velocity should both be positive. Is that the case? Yeah, so it matches that rule of thumb, right? We can prove it always mathematically too, but I want you to kind of just be checking with yourself as we go through that. Okay? Questions about how those numbers went in? Right? Once it goes in, it's very simple math. We just have to make sure we get the variables and the numbers in the right spot. That's the trickiest part. Okay? All right, try this one on your own. Car is moving at a speed of negative, sorry, the negative got cut off here, negative 28.6 meters per second. She slows to a speed of negative 24 meters per second over a period of 3.2 seconds. What is the acceleration? Okay, so you might want to move that negative. It accidentally didn't go on the correct line there, but it should be negative 28.6. She slows down to negative 24.
She's going backwards.
That's right. Yeah, south or west. My acceleration in this case came out positive. So I want you to think, was she speeding up or slowing down? She was slowing down, right? She went from 28.6 to 24. Even though those values are negative, it has nothing to do with the numerical value of it being negative, right? 28 meters per second is faster than 24 meters per second. The negative just tells us direction. So she was slowing down in the negative direction. So does it make sense that my acceleration came out positive? Yeah, right? It's the rule of thumb. If they're slowing down, my velocity and my acceleration have opposite signs. My velocity was negative, so my acceleration should be positive.
Does that mean she was just going in reverse?
Okay, a car moving 75 kilometers per hour comes to a stop in 5 seconds. So do we see some issues here? Are there some red flags going up? What's the first one?
There's no final velocity.
Okay, there's not a number given, but what do we know about coming to a stop? 0. that my final velocity would be 0. So I like to make the list, right? Especially as we start getting more variables, I might start making a list over here. My initial velocity is 75, but it's in kilometers per hour. So do we see a problem with that and with our time? Time is in 5 seconds. So now do you remember the shortcut to convert kilometers per hour to meters per second? We're going to divide by 3.6. That's our shortcut to go from kilometers per hour to meters per second. So 75 divided by 3.6 gives us 20.8 meters per second. Okay, from there, I can go ahead and plug it into my acceleration equation. Acceleration equals 0 minus 20.8 over 5. How many of you remember to put the 0 first? Right? Okay, very good. We want to be careful there because a lot of times when we only have one number, we like to put it first, right? But we've got to be thinking about we are really slowing down in the positive direction, which means my acceleration needs to be negative. So 20.8 divided by 5 gives me a value of negative 4.2 meters per second squared.
Does it matter how we round these?
No, not really. I'm just trying to look at significant figures. So I started with 2 on each of those. I'm trying to I want you to try to be within probably a significant figure one way or the other. You know what I'm saying? So I'm not going to be really a stickler about it, but if we start with 2 significant figures, I'd like your answer to have between 1 and 3 significant figures, if that makes sense. I'll kind of give you 1 on either side with wiggle room for that, okay? Which most of the time we always are anyway, just naturally rounding that, but just be a little bit cognizant of it. Okay? Any questions there? Does it fit the rule of thumb? Slowing down in the positive direction, so my acceleration is negative. All right, I want with the person next to you to answer this question. Discuss this for just about 30 seconds, and then we're going to come together and see what we think. If the acceleration of an object is 0, does that mean that my velocity is 0? Yes or no?
Cruise control.
Yeah, very good. Okay. If my acceleration is 0, that simply means my velocity is unchanging. It doesn't necessarily mean that I don't have any velocity. It just means that it's unchanging. Okay. All right, let's move into what I call now our, we're going to get 3 big equations. Okay, and you'll hear me call them the big 3. Okay, and they are called equations for kinematics. Okay, so maybe I want you to label them on your equation sheet. These are your kinematics equations.
Velocity is also kinematics, right?
Velocity is part of kinematics. What's kina mean? What's that?
Motion.
Yeah, it means motion, right? So these are equations for motion. So you've got 3 equations for kinematics, and they're kinematics for constant acceleration, but you don't need to necessarily have that last part. But I want you to label them as your kinematics equations, and you're going to have 3 of them. Okay? These 3 will be much more important than the baby velocity and baby acceleration equation that we just learned. Okay? These 3 will be much more important. Okay? So here is our first one. VF equals VI plus AT. These big 3 kinematics equations only work if we know that our acceleration is constant. Okay, so what that means is that if we've got situations in which we speed up and then we slow down and then we do something else and then we do something else, we can't do that in one equation. That's all that we're saying here. We have to split our motion into the portions that have constant acceleration. So if we speed up for 3 seconds, then we slow down for 3 seconds, we have to do those in separate equations, right? We can't do that in one because these equations have to have a set of constant acceleration. You might have to solve for what that constant acceleration is, but it's got to be constant through that time. Yeah. These variables are the exact same variables as the acceleration equation I just gave you. Okay, that's because if you take this equation, A equals VF minus VI over T, and you rearrange it, times T plus VI plus VI, doesn't it look the same? VF equals VI plus AT, right? That's why I think this one is more applicable than the acceleration one I just gave you. This one we'll use more often. Okay, but what does VF then have to mean? Final velocity, initial velocity, acceleration, and time. Okay, so we know what all four of those things mean. Let's go ahead and try some equations with it. It's similar questions to ones we just saw, right? Because the actual variables we're using are the same. Okay, a bus traveling at 30 kilometers per hour speeds up at a constant rate of 3.5 meters per second squared. What velocity is it at 6.8 seconds later? Okay, so I'm going to start encouraging you to start making that list of those variables kind of in the margins here. I'm going to encourage you to listen real quick, okay? I don't want you to just automatically list out every variable. I don't want you to do VF equals, VI equals, A equals, T. I don't want you to do that because we're going to start getting variables that aren't used in every question. So I don't want you to have variables there that you don't need that might confuse you about what equation to use. So I want you to take them from the problem and assign them their correct variable. So I'm traveling at 30 kilometers per hour. That has to be my initial velocity. So I'm going to take that and put it down. I'm speeding up at a constant rate of 3.5 meters per second squared. Just the unit itself should tell me what variable is that. It's acceleration, right? We're starting to use just the units to identify that. So 3.5 meters per second squared is my acceleration. And it says there's my time, 6.8. It asks me for what velocity is it at. So what variable does that have to be? Okay, and then I'm just going to put a question mark there so I can really tell myself what am I supposed to be solving for. Okay, I'm going to encourage you to list your variables as they come up in the problem. Don't make yourself the list first and then fill it in. Okay, that seems like a really minute detail, but as we start getting in problems that have greater amounts of variables, you'll start to kind of confuse yourself if you make the list first. So, what do we need to do with that 30, first of all? Right, we got to take it to meters per second, so what's our shortcut? Good, divide by 3.6, and so that gave me 8.33 meters per second. Okay, so if I go plug that in, I'm solving for VF, so I leave that. Initial velocity is 8.33 plus acceleration times time. Right? Then it's just plug it in. Once we get all those variables assigned, then we're just plugging it into the right equation.
Do we ever have to worry about the final velocities, units, or are they always going to be meters?
As long as your initial velocity units are meters per second and your acceleration units are meters per second, that's what it's going to come out in. Yeah. I got about 32.1, yeah. And so if I look, I started with 3 sig figs on my velocity, so I can leave it there probably for my meters per second. So this is number 2. Okay, kinematics number 2 of the big 3. This time we've got 2 new variables. XF, where have we seen that before? Yeah, it's like position or it's displacement, right? So this is like, think of it as final position. And this would be initial position. And what do you think both of those will be measured in? Meters. Going to be measured in meters. Okay, so now here's something I want you to be thinking about. Do you remember when we started talking about motion at the very beginning, I said I like to set my origin at where my motion begins. Do you remember when I said that? And here's the reason why. I like for my initial position to always be 0. Right? Because that drops a variable out of the equation for me. I like my initial position to always be 0. And then when I solve for my final position, that tells me where am I ending up in relation to where I started. Am I below where I started? Am I above where I started? To the left or to the right, right? It tells me in relation to where I started that my final position is positive, negative, whatever it is. So if we look at, something that, I don't know, I like to use something on a cliff example, right? We throw something off a cliff here to the bottom. I like to set my origin here, and then my final position will be negative, right? My final y position would be negative. My final x position would be positive because I was below and to the right of where I started. But in this case, by starting my origin here, my x initial would be 0. Okay, so I like to make sure we do that. It's going to be very rare that we actually have an xi that's not equal to 0 if you want to set it up that way. If you don't, fine. Okay. All right, let's try one here. A train accelerates from rest at a constant rate of 3.15 meters per second for 1.57 minutes. How far does it travel in this time? Okay, so let's start identifying these variables here. It accelerates from rest. Is that important? Yeah, so what is that from rest? What variable does that need to be assigned to? Initial velocity is 0. Okay, it accelerates at a constant rate of 3.15 meters per second squared, which means it has to be my acceleration. And it has a time of 1.57 minutes. And so what do we see as an issue there? We're in minutes. So we need to put it into seconds. So easy conversion there. What do? Just multiply by 60, right? I got 105 seconds. Okay, so now it asks us how far does it travel during this time?
It's 90.57.
Oh, I did 1.75. I'm sorry, you're right. Thank you. Tell me what it is.
94.2.
Yeah, thank you. 94.2 seconds. Thank you. Okay. It asks us how far does it travel. So tell me what variable does that mean we're solving for? VF would be how fast is it going? Yeah, XF. There we go. XF is going to be my question mark. So you can start labeling XI as 0, or you can leave it out of your list knowing that it's 0, right? Because I don't really care what happened to my train before we started marking this. Right? What I'm concerned with is the time it goes from 0 meters per second to however many meters per second. Did you notice what variable is missing from this equation? Final velocity, right? We don't care what the final velocity is. So if we're given a problem that we don't have final velocity, this is the equation we probably need to use, right? So let's go ahead and plug it in here. X final is what we're solving for. X initial is 0 plus VI times T. Times T, 94.2 plus 1/2 A 3.15 times T squared, 94.2 squared. Sorry, that kind of gets dark up there at the end. What I want you to recognize here is that in this equation, only the 94.2 is what is being squared. It's not the whole term. So it's not 1/2 times A times T and you square that whole term. It's just time that gets squared. Okay? So these two first terms, I'm just dropping these out, right? They're both 0. Because my initial velocity was 0, anything times 0 is 0. So X final is equal to 1/2 times 3.15 times 94.2 squared. So tell me, does that answer seem reasonable? Okay, if we're speeding up at a rate of 3.15 meters every second. So we're moving here with this train. And this happens for a minute and a half. So you've got 90 seconds worth of this train really gaining speed. So it should make sense at least that our final position is large, right? You don't have to be able to predict the range it should be, but I want you to be able to think about the fact that they really sped up a lot in that 90 seconds, and so that caused them to cover some distance there. Okay. All right, why don't you try the next one here on your own? Can we do this problem in one equation? No. We've got to solve first for acceleration, and then we can move in to solve our final displacement. Did you guys recognize that? You can use, what equation can we use to solve for acceleration? The first one, right? And then we'll have to use the second one to solve for final position. So kind of get used to the order that those equations are written in, because we'll reference them as the first kinematics equation, the second kinematics equation, right? So I'm going to use the first here to solve for acceleration.
If you know the x and y is 0, can we just leave that out?
Mm-hmm. Yep. Yeah, I don't mind if you just drop that term from the equation altogether, as long as you just know it's there if you need it, but it'd be very rare that we need it. Velocity final squared equals initial velocity squared plus 2a times delta x. Okay, or what's another way you could list that parentheses if you wanted to? You could say x final minus x initial. Right? If that makes you more comfortable, you could list it that way. Knowing what we know about x initial, right? It's going to be 0 most of the time. In all reality, it'll most of the time be 2a times x final, right? That's most of the time how you're going to solve that problem. I wouldn't necessarily write your full equation like that, but I want you to just be aware that most of the time x initial is just going to be 0, so we're going to drop that out of that part of the equation, right? What variable is this equation missing? Time, right? It doesn't have time. So if you're given a question in which you don't have time, right? It wasn't given to you. This is the one you'll need. So we've got equations for every situation, right? The first one doesn't have any position requirements. The second one doesn't have a final velocity requirement. And the third one doesn't have a time requirement. So now we're able to manipulate the set of these three equations to really be able to solve for anything that we need. Okay? Let's try this one here, and then I want to, then we'll have to stop for today. But a car starts at rest and speeds up at 3.5 meters per second squared after the light turns green. How far will it have gone when it's traveling 25 meters per second? So let's start identifying our variables here. Starts at rest tells me VI equals 0. 3.5 meters per second squared, what's that tell me? Acceleration, good. 3.5. How far will it have gone? What does that mean I'm solving for? Yeah, good. X, F is my question mark. And then it tells me when I'm moving 25 meters per second. So that's my final velocity here. So I don't have time. So I've got two options. I could either use the information I have to use the first equation to solve for time, then use the second equation to solve for XF, or I can just use the third and do it in one, right? So there's always workarounds to get to your final answer. There's always more than one path to get there. And sometimes you'll miss it and you'll do more work than you have to, but you'll always be able to get to that final answer. Does that make sense? Like, you might miss the right equation the first time, but like, if you do more work, it's not that big of a deal. It'll still get you there. So I know I can use my third one though. So 25 squared equals 0 squared plus 2a. And then I'm solving for x final, but do I need to put x initial into my equation here? I don't, because I know it's 0. And so if it's 0, I can just leave it out of that subtraction part of the equation. Okay, so 25 squared is 625, I think. Okay, so 625 equals 7 times xf. I'll divide over that 7. And I get an x final of 89.3. That's fine. 89.3. And what are my units going to be for XF? Always meters. Okay, always meters.